the slides back up again? Yeah, okay. Right, so for the second talk of this session, we'll have Marten Folkertsma talking about quantifying Grover speedups beyond asymptotic analysis. Take it away.
Well, thank you very much. I want to start my talk by thanking the organizers for organizing this great conference. I'm Marten Folkertsma, as you can read over there. I'm a PhD student at QCTIP at CWI, together with Javi Buurman. I'm here today to give a talk on work that I did together with Chris Kay and Ido Niese, who are somewhere here in the audience, you might know, and Jordi Wegman, who sadly couldn't make it today. Let me see. Yes, the slides work. And the name of our talk, as you can read, is Quantifying Grover speedups beyond asymptotic analysis. So I want to start my talk by actually discussing a problem that hopefully is well known to all of you, and that's the traveling salesman's problem. In this problem, you are asked, given a set of cities, to find an optimal route through all these cities, such that a salesman traveling from city to city has to traverse the least amount of distance. And as you probably all well know, this problem is in general NP-hard, so it's really hard to actually solve. And solutions have been found, or algorithms have been found in using classical computers, using dynamical programming. But of course, because it's NP-hard, if we want to solve every single case optimally, this can only be done by running an algorithm that takes exponentially long. And Mbinus has shown that given this algorithm, we can actually speed it up using a quantum algorithm that has a better scaling in the asymptotics. And actually, from going from 2 to the n, he showed that we can go to a scaling of 1.68 to the n, which is a massive speed up in large n, but still really, really slow if we actually want to solve these problems. However, if we then look at what people actually do in practice, when they are maybe not so interested in finding the very optimal solution, but just something that is really, really good, they tend to not use these type of algorithms that are really that have the best worst-case scaling, but they use different algorithms called heuristic algorithms, and in general have a terrible worst-case runtime, but end up being really fast in cases of actual practical interest. And what we observe here is that at some point, maybe we want to use these quantum algorithms that we've developed to actually solve these kind of problems. But at that point, we probably won't go up against these worst-case runtimes, to which we can already prove like great speedups, but we will have to compete with these classical heuristic algorithms. And what we wonder is, can we somehow compare these two? Like classical heuristic algorithms and quantum heuristic algorithms, and find out in some way if our quantum heuristic algorithms are actually faster than their classical ones. So our question is how to compare runtime. Well, first I want to kind of sketch the field that we are in right now. So I already talked about this a little bit. Worst case analysis is one option to compare runtimes, which is really good if you look at super large problem sizes, because it especially works very well in the asymptotic limit. But it might not be very representative of actual real world cases, as we see in heuristic algorithms. On the other hand, what we can do is we can take our algorithms and write down a circuit and actually simulate these circuits, as was very well talked about in our last talk, which is really good if we want to have something representative of real world runtimes, because we can just plug in whatever instance we're interested in. But it's not so good if we want to consider very large problem sizes, because we're severely limited by the classical computer simulating this circuit. On the other hand, I think we all agree that the end goal will eventually be to actually use fault-tolerant quantum computers and do experiments on these devices, which will allow us to plug in whatever instance we're interested in, and also allow us to go to large problem sizes. However, even though we've seen great advances in this direction during this conference, you probably all agree with me that this is still quite far away, and we cannot actually do this yet. So what we hope to do is to get somewhere in the middle, where we can already consider semi-large problem sizes, and at the same time keep them quite representative of real-world runtimes. So to that end, we ask ourselves the question, can we construct a method that allows the comparison between runtimes of classical algorithms and quantum algorithms on instances of practical interest? And just to simplify the problem a little bit, And to clarify, in this case, here in this talk, I will be talking about runtime. Whenever I say runtime, I will be talking about queries to some function. All right. Before I try to answer this question, I kind of want to discuss what type of algorithms we're looking for. So we're looking at quantum heuristic algorithms. And actually, the type of algorithm that we will be using will be of a Grover type speedup. So we take a classical heuristic algorithm, let's say a hill climber. And in a hill climber, what happens is we start at a randomized point, somewhere in our solution space. And then the first step is to kind of search around in this solution space for a direction that actually gives a positive increase to some cost function. And this search we replace by, instead doing a classical search routine, we replace this by a Grover type search routine and use kind of the quantum, use a quantum search routine instead. So what will happen is our Grover type search routine will give us a direction to kind of walk in. And what we get is we get a direction and we can slowly start walking up this mountain. And what we see is that for every step, we have to rerun this kind of search type algorithm. However, if I start in the same position again, and I rerun my algorithm, what can happen is that instead of finding a direction to the left, I can find a direction to the right. And in this direction, I can totally optimize my cost function. And in the end, I will, of course, reach a peak. But this might take a couple of extra steps during the total run of the algorithm. So something that we already noticed just from this tiny little picture is that especially in heuristic algorithms, the number of steps is known in advance and depends on random choices during the operation of our algorithm. And this kind of gives a little bit of a hint that we cannot just use worst case analysis, and we actually have to kind of look at what actually happens and run these algorithms to kind of figure out how long they will actually take. And another thing that we note is that in these types of algorithms, we have a per step speedup. So questions that naturally arise is how much of the per step speedup actually manifests itself when we look at the application of this algorithm. And another question, and especially for particular cases of practical interest. And of course, we kind of wonder in the end for what sizes of problems we would actually expect a speedup to be found. So how do we do this? Well, as I already mentioned, we have this heuristic algorithm, and we replace our search parts with quantum search routines. So the two search routines that I will kind of highlight today, but there are more in our paper to be found, are groups with unknown number of marked items and quantum max finding, which the first one was first proposed by Boyer in 1998, and the second one by Doer and Boyer in 1996. Now, I kind of motivated that we sort of have to run this algorithm to actually find out how long it takes. But of course, this is not possible because we don't have these fault-tolerant quantum computers yet. So what we suggest is because we know that these algorithms are at most quadratically faster and in general polynomially faster, we can actually just simulate them by a classical simulator. So in our calculations, what we do is we replace the quantum subroutine by a classical subroutine that does exactly the same thing and simulates the exact behavior of the quantum subroutine. But at the same time, what we want to do is we want to gather some information about the search steps that we actually perform, and using this information and using rigorous bound on the expected number of queries that our quantum subroutine would have taken, we can figure out by doing this simulation how long our quantum subroutine would have taken if we would have run it instead. So to reiterate, we have this quantum heuristic algorithm, we simulate it by a classical algorithm, and we use information that we gather along the way to figure out how long the quantum subroutine would have taken if we would have run it instead. So the type of information that we need is, of course, at any given moment, the size of list that we're actually searching over, which is often given by the problem instance, the number of marked items that are in this list, which can be gathered in two different ways. It can either be determined exactly by doing an exhaustive search, so literally checking every element if it's marked or not. Or if you're lucky and your problem has some local structure, it can maybe be kept track of during the updates of our algorithm. And this is actually what we use in most of our simulations that you will see. However, if we go to very big problem instances, both of these methods probably become completely intractable. And what we do is we can take a number of marked items through classical sampling. The third parameter that we kind of need is the error probability. This is the probability with which we allow a quantum algorithm to fail. This is kind of necessary whenever you run a quantum subroutine. And this is determined by the number of steps that our algorithm performs. And the fourth parameter is actually when you implement these quantum algorithms, and when we kind of did the calculations, we found out that especially in a regime where there's very many marked items, so a very high fraction of marked items, it might be kind of inefficient to actually run the quantum subroutine, and it's more efficient to run a classical subroutine instead. So this is kind of given by this, this number we call n samples, which says that before we actually start running quantum subroutine, we allow ourselves to do a couple of classical sampling in the running of the actual subroutine to kind of differentiate between this fact of being in this situation of having a lot of marked items or having very few marked items. And we give this as a hyperparameter to the algorithm, which we can then optimize. So what kind of bounds do we then actually get? Well, of course, this is kind of the thing that we're all used to and what you kind of see in every theory paper. Ooh, sorry. But then if we actually, when we looked at grovers with the known marked items, for instance, we redid the analysis and gathered out all the constant and all the log factors necessary to kind of figure out how many function calls you would have taken, would you have run it instead. And then instead of this very neat and nice expression, we get something of the form of such an expression, which is much more difficult. And I will not go explicitly in what's written down here. But the good thing is that basically what it is a function where I plug in 4 parameters, which I can just put into my computer. And if I have these 4 parameters, I can figure out how long my quantum subroutine would have taken. Okay, then there's 2 more points that I kind of want to iterate. And that is that the allowed success probability is dependent on the number of applications of the subroutine. So the number of times that we go on this search routine. And this is often not known in advance, as we've already seen in this very simple example of the hill climber. So if we actually want to do this, we somehow need to have an estimate of how often we run the subroutine, because otherwise we cannot give this error probability to our simulator. And this has to be actually an upper bound on the number of steps that you actually try to make, because otherwise there might be a moment wherein your subroutine starts failing and you're not guaranteed of finding an answer in the end. Luckily, you can get this through classical sampling. Maybe it's better to do it in the end. You can do this through numerical simulations. And the second point that I kind of want to state is that small polynomial speedups mostly manifest themselves in very large problem sizes. And this requires an efficient method of keeping track of the number of marked items, which is already discussed before, can be done by doing classical sampling. So now I've described kind of our setup and our kind of idea of how we want to analyze these algorithms. It's maybe fun to actually see how this actually works in practice. And what we took is, as a use case, we took the use case of community detection. But let me first describe what is community detection. In community detection, you're given a graph with all nodes and kind of connections, and you're asked to find a partition of nodes such that nodes that are very highly connected to each other are in the same community, and nodes that are very loosely connected from each other are in different communities. This question is actually rather important because it has applications in many different fields, such as the study of social networks, the study of recommendation systems, transaction networks, and many other things like biological studies. And it's used a lot in practice. So to kind of clarify this problem a little bit more, the task is, and put it a bit more in a mathematical framework, Our task is to find a partition of nodes given by a function we call this L that maximizes a optimization, a objective function which we call the modularity, QL. And I've written down what the function is here. I will not dive deeply down in what this exactly means because it's not really necessary. But basically, this kind of captures this notion of nodes that are very closely connected to each other. If you put them in the same community, this gives you a positive contribution to the modularity. And if they are if they are very loosely connected to each other and you put them in the same community, then it gives you a negative contribution to this modularity. And it has been shown by Brandes and all that actually optimizing this modularity is NP-hard in general. So you're not going to find a method to actually solve this in every case. But then, as I already said, it's kind of useful in many applications. So what people do instead is they use heuristics to solve this problem. And the heuristic that is like most studied, as far as we know, is called a heuristic algorithm, which is called the Louvain algorithm, which has been cited for, I think, over 10,000 times. So it's something that is actually being used quite a lot. I will shortly describe what this does. So the Louvain algorithm, it randomly assigns communities to every node. Actually, it puts every node in its own community, and then it does a random search on all the nodes, trying to move one of the nodes to a community of its neighbor. And if this gives a positive increase to my modularity, then it does it. And if it gives a negative increase to my modularity, then it does not. And it reiterates this process of doing a random search over all the nodes until it cannot find any node anymore that would be that if I move it gives me a positive increase to the modularity. And here we already find this structure where we have to do many steps of unstructured search over quite a large search space, because the search space will be the number of nodes that are in the graph, which can blow up to very, very large graphs. So to analyze this, I put down here the Louvain algorithm, and I gave a notion of its complexity per step. So every time that we run this search part, what's the complexity? I will not explicitly say what these parameters mean. This is not very relevant. It's more to see how we can construct a quantum algorithm that has a very strong asymptotic scaling and kind of compare these two together. So more importantly, we actually run this algorithm on power law graphs, which are graphs that are typically very representative of social networks and biological graphs. Just run them and kind of plotted how many queries the Louvain algorithm made to this modularity function. So in the graph, we see at the bottom, we see this number n. This is the number of nodes that are in the graph that we at that point looked at. And on the y-axis, we see the number of queries. And this is the number of queries that were made to the modularity function. On the top, just to say it for a second, D here is the average degree. So these graphs are relatively sparse. And mu is a factor that kind of controls the amount of community structure that is in the graph. So the first thing that we thought was we took the Louvain algorithm and we actually found a direct speedup on it. We kind of took all the structure of the Louvain algorithm and tried to build a quantum algorithm that exactly mimics its behavior. And it gets this complexity per step, which is like a direct asymptotic speedup where we have this beautiful square root. But then if you actually run it and kind of test it, what we see is that it performs much, much worse than the classical algorithm. So in number of queries, it's much worse than just running the classical algorithm. And one of the reasons for this is actually that there was we made use of a nested Grover loop, which is basically first I search for a node, and then whenever I found a node, I kind of want to look at the neighbors of this node. And this gives me a double layer of Grover iterations. And especially in sparse graphs, this might be very expensive because we want to know for sure that this inner loop kind of succeeded every time we make a call to it. And this requires a lot of boosting. So for sparse graphs, we made a different version where we kind of took out this inner Grover loop and just replaced it by a classical loop. And what we found is that this already performs better than our original version of quantum looping. SG, the suffix, stands for sparse graph, just to make it a little bit more clear. It performs better, but it's still much worse than the actual classical algorithm. So what I already said is that the first version kind of directly mimics what the classical algorithm does. And what we found is that there is some searching. One thing that it requires is that it searches over a list and tries to find the first element of such a list to kind of update this. And this is not really necessary whenever we do a quantum version of this. So we release this constraint and just let the quantum algorithm search over the whole set of nodes. And by this doing so, we constructed a new algorithm called simple quantum looping. And again, we have one with an inner Grover loop and one without. And what we see is if we actually run it, it starts performing a little bit better, but still much, much worse than the actual classical algorithm. And this is only inquiries. So in our last step, we kind of started looking at the problem a little bit differently. And instead of searching over the space of nodes, we started looking on the space of edges, where if we select an edge, we select one of the nodes and try to move it to the other node in the edge. And we started to search over this space and created a final quantum algorithm, which we call X2Q-looping. And by doing so, eventually, we finally found an algorithm that in a number of query counts on these given graphs outperformed the classical algorithm. Although still it's not much faster than the classical algorithm as we would have hoped. This is tests on parallel graphs, but in our paper we also looked at different graphs, and the same kind of picture kind of arose for whatever we kind of studied, and also for different parameters of that. So besides doing this on artificial graphs, we also looked at some actual data sets and graphs of actual data sets, such as the academia graph, the DBP-L graph, and the Amazon graph. And we ran our classical algorithm on this, the classical Louvain algorithm. And here the total queries must be multiplied by 10 to the 7. And what we see is that this HQ Louvain outperforms this Louvain algorithm, but only by about a factor of 3. And this simple Q-Louvain version was like totally left behind by the classical version. So what can we learn from this? First of all, more complicated quantum algorithms, such as ones that have like an inner Grover loop, might be much less, might work, even though they give a better asymptotic scaling, they might perform much less well if we actually apply them in practice. And especially these inner Grover loops, kind of, because it requires us to boost it very often, this really slows down the algorithm. And our original quantum looping algorithm required us to kind of look at sets and verify that these were empty. And this is really hard to do using a Grover type algorithm, because this again requires to basically never fail. And this is very costly. And this is what you see why this original algorithm was much slower than the second one. And thirdly, as we've seen, first we started searching over the set of nodes, but then it looked like more beneficial to start looking on the set of edges. So it's very important to identify the exact search space that we're looking on and try to directly apply the quantum algorithm on this search space. And the fourth point that I kind of want to mention is more inherent to the problem itself. What we found is whenever we did this problem and kind of looked at how often, at the fraction of marked items that we found during the update algorithm, what we found is that for the majority of the algorithm, there were actually a lot of marked items. The fraction was really high. So in this case, it was actually not so useful to use any Grover search steps. And we mostly used classical search steps, as I already mentioned, by using n sampling. And only at the very end, you found a regime where there were very few marked items. And in this kind of stage, the quantum algorithm could outperform the classical algorithm. But this is kind of why you see not such a strong speed up, because there's only a very small regime in which the quantum algorithm actually outperforms. All right, let me conclude. So first, let me summarize. What did we do? We provide a framework for estimating runtimes of quantum algorithms that achieve modest polynomial speedup over their classical counterparts using Grover-based routines. This allows us to estimate runtimes of these algorithms on actual data sets, as we've seen with academia dataset. And thirdly, through the use case of Louvain, what we found out is that we can actually use this method to kind of design algorithms and kind of figure out where they are useful and where they are not, to kind of simplify them down and find out where we can actually apply these search steps. So what we would like to look at in future work is actually here in this study, we only looked at query counts. But we think that this method of simulating the quantum algorithm, given some information of the classical algorithm, naturally would extend to also building in gate counts, or maybe even actual runtimes, given these estimates by, for instance, the Google papers. And furthermore, we did this for Grover type algorithms, because this is kind of the most basic premise that you can look at. But we think that this method kind of naturally extends to other algorithms that also have a classical counterpart, such as, for instance, quantum random walks, or maybe other algorithmic primitives. And lastly, what we think is that this might actually be a lot of fun to integrate with already existing software packages. That somebody can design an algorithm with having these search steps in there, and you can just give it to the software package. The software package actually runs it, uses these bounds to kind of estimate how long the quantum algorithm would have taken, and kind of directly gives you back, like, how much faster am I than my classical counterpart? All right, with that, I kind of want to end my talk, and thank you for your attention. And if there are any questions, please give them now.
Thank you very much. I see we've got a question here.
Yes.
So the numbers you put up there are runtime, that's correct, right?
Runtime in query, so it's query count, queries to the modularity function.
Do you know how good the solutions of the different methods are compared to each other?
Oh yeah, I didn't put it here, but you can actually look at it by just calculating the modularity, and they are roughly the same. Okay. Basically, all of them are actually the same.
And a quick follow-up question: if the edge Louvain or the quantum versions of the Louvain algorithm only really require quantum computer, like this very last bit, is that something that can maybe be split up and uploaded to a classical simulation to get like a classically inspired improvement of the Louvain algorithm?
So what you mean is basically if we only gain something on these very last steps,
yeah,
can we take this part,
yeah,
and run it on a classical simulator?
Yeah, or yeah.
I'm not 100% sure, but in principle, I don't really directly see why this would not be a problem, except that these algorithms also have a data structure that you kind of have to upkeep to allow yourself to do these updates. And it might be that you kind of need to switch from one representation to another one, and I'm not sure how costly this is. So you might lose all of your speed up there, but in principle, it might help out. Yes.
There's another question over there.
So about the edge on Louvain.
Yes.
Did you ever try to upgrade the classical algorithm to search over edges instead of this?
Yes. Funnily enough, in total steps.
Sorry, let me just read the question for people online. So the question was about upgrading the classical algorithm to also search over edges rather than vertices in the same way as the quantum edge Louvain.
Yes, we did. The only problem is that the way that the original Louvain algorithm works is one of the major advantages that it has a very clear termination procedure. Basically, it looks over randomized lists, and whenever it hits a node that it wants to update, it updates this. And if you then do your final run through, whenever you end the list and you did some update alone, you just re-randomize your list. And then in the end, it just runs through a list one time and it knows that there's nothing to update. And in this quantum version, we kind of do this randomized search procedure. And this gives you a bit of a harder time to kind of figure out what kind of how to terminate your algorithm. Yeah, what your stopping criterion is. And this kind of worsens the classical algorithm quite a bit. Though you could do the same thing with like a list and edges. We did try this, but it gives like a similar result as the original version.
Ashley.
Did you do any kind of fit on the runtimes of these algorithms then to work out what the sort of empirical asymptotic complexity is?
Yes, we did. I kind of
repeat the question again.
Sure.
Okay, so this was about whether you did any fit on the graphs to figure out what the empirical asymptotic runtime should be.
Yes, we did. It's in the paper. I kind of plugged it out because it was a bit of too much information on the slide. But what I can say is we did a fit in these log-log plots. And then compared like the quantum algorithms versus the classical ones. And what we found is, no, I don't. Okay, so the quantum Louvain and the quantum Louvain SG actually lose even in asymptotic scaling to the original algorithm, which at some point they should not, of course, because we have this like asymptotic result, but this is like beyond the scope that we actually tried these algorithms. And we see that the HQ Louvain and the simple Q Louvain are very similar in like their advantage. I think it's like, so if you divide the coefficient by the original coefficient of Louvain is like 1.2 or 1.3, something like this.
Okay, we're a few minutes past 12, but we started late, so let's thank the speaker again.